Welcome once again to Humke's Study. Today we're going to take a look at this problem. I give you three vectors, u1, u2, u3. They're all in four-dimensional space. And I ask you to find the subspace spanned by these vectors. So the word find is what we're talking about here. I really want to know what this is. There is a clear answer to this and an easy answer. The answer is the span of the three vectors. So if you look the span of u1, u2, u3, literally this is the answer to this question. This is the subspace spanned by those three vectors. But it doesn't give you really much information. So I'd like to take a look at what we've done already and give another way to do this problem. So I'm going to put these vectors into a matrix, minus 1, 2, 3, 1, minus 6, 7, 5, 2, 4, minus 3, 1, 0. I'm going to row reduce this matrix, see what we get, and this will give me information about the span of those three vectors. So let me take a look at that here. Okay, here we go. 1, 0, 2, 0, 1, minus 1. 1, 0, 2, 0, 1, minus 1. 0, 0, 0, 0, 0, 0. So this matrix gives me information about these two because of where these pivot positions are. These pivot positions will tell me, there are only two of them, first of all. It tells me that these two vectors are linearly independent. And so the span of all three of these is the same as just the span of the first two, because this one is already a linear combination of these. So the answer to my question, I'll say answer 2. Answer 1 was the span of all three. Answer 2 is the span of just the first two. And U1 and U2 together are linearly independent, or that is a linearly independent set. This is better information. Because these two are linearly independent, it tells me that the span, the subspace of R4, is a plane. And the dimension of it is 2. So this is a better answer. And the basis for this judgment, or the basis for this answer, is just these two vectors and the fact that they are linearly independent. So a basis for saying that, this is a plane and its dimension is 2, is this set of two vectors, which we know is linearly independent. So it's a basis for our judgment. Now we had all three, but those three didn't let us conclude very much. Only that the span of these three was what I was after. But the actual description is based on the fact that these two are linearly independent. Now, there are many ways, any two linearly independent vectors in this span would have been a basis for that same judgment. And what I'm going to show you next is an alternate way of doing this same problem that will give us a separate basis for the judgment. It'll be the same conclusion, but it'll be a different basis for that judgment. So let's take a look at that. So I'll call this method 1. We've already looked at this. The only thing new about it is this: when we reduce it, I called this a basis for the judgments we're making. Okay, so let's look at another way to do this problem. The second way is interesting. There are many ways to do this problem, and we'll look at least 3 of these methods during the course of the course. So method 2, we're going to put these vectors not in the columns, but in the rows. And I'm going to row reduce again. And I'm going to do the first, to show you what's going on here, I'll do one of these row reduction methods by hand. So I'll take 4 times row 1 and add to row 3. So that's one of the things you can do in this row reduction method. When I do that, the first 2 rows stay the same. And the last row becomes 0. 4 times 2 is 8, minus 3 is 5. 12 plus 1 is 13. 4 plus 1 is 0. So this is what we get. But the key is that anything that was in the span of these 3 rows is in the span of these 3 rows and vice versa. And the reason is that the last vector here that I got was a linear combination. In fact, that linear combination of 2 rows from over here, in this case, the first and the third. Viewing these as vectors, 4 times this plus this is a linear combination of these. All of the elementary row operations that we've studied, we've talked about, do that. They create linear combinations. And so because these 3 rows were all vectors in the subspace I'm talking about, all 3 of these rows are in that same subspace and vice versa. And that's true for every step of the row reduction, including the last step, which is the reduced row echelon form. So when I reduce this matrix, reduced row echelon form of this matrix, all of these rows will still be in that span of these 3 because they'll be linear combinations. And so let's see what we get here. 1, 0, 11 fifths, 3 fifths. And the second row is 0, 1, 13 fifths. 4 fifths, and then 0, 0, 0, 0. Now, it is obvious now that these 2 vectors are linearly independent because of this hierarchy of zeros and ones. This is called a step. And the last row of all zeros is 0 is always dependent on everything. So it's easy to pick out the 2 linearly independent vectors, or 2 linearly independent vectors that span the same thing that these do. So the span of, I'll write things out as rows here, the span of these 3 rows, minus 1, 2, 3, 1, minus 6, 7, 5, 2, and 4, minus 3, 1, 0. The span of those 3 is exactly the same as the span of these 2. It shows you that there's this 0 row says there's 1 redundancy among these in terms of linear combinations. And so the 2 vectors that remain, the 2 vectors I put in blue, these 2 vectors also are a basis for the judgment that the subspace spanned by these 3 is a plane, and it's spanned by just these 2, and the dimension of it is 2. So I'm going to erase this except for this that I need to write on and write the conclusion. So the span of these three, the span of U1, U2, U3 equals the span, just these two. I'm going to write these as rows in this case, 1, 0, 11 fifths, 3 fifths, together with 0, 1, 13 fifths, 4 fifths. So a basis where, so the dimension of this subspace is 2. Two linearly independent vectors span it. And this is a plane, and so this is a plane in 4 dimensions. And the basis for this judgment is just the two independent vectors, 1, 0, 11 fifths, 3 fifths, and 0, 1, 13 fifths, 4 fifths. So this is method 2. There is an advantage of method 2 over method 1 in that if you just see these two vectors, it is clear that these vectors are linearly independent because of this step down. And so it is clear that these are linearly independent just by their positions. So in a sense, you can just view it and see that these are linearly independent. You can't necessarily see immediately that this span is the same as this span, but once you know that these vectors span it, you know they're linearly independent, and so you know that they are a basis for this judgment that the dimension is 2, and so this is a plane in R3. This is called a stepped basis for that reason. The other basis is just a plain old white bread basis for judgment, but this is a stepped basis, and it has a particular form. So I'd like you to take a look at that next homework assignment with this in mind. This is an example of how to work these by the 2 methods. The first problems ask you to do that. We will be finding various bases, so I'd kind of like you to learn both methods, but particularly this method 2 will be advantageous for us. And so I will see you tomorrow.